Here's the solution to homework set number 3 for ECE 320, Electronics 1. The first problem is a repeat of a problem from homework set number 2. Given a diode with a 100 ohm resistor and 5 volt source, find the voltage and current. With this one, we're going to assume an ideal diode. An ideal diode, the diode is either on or off. If it's on, this part of the curve, the voltage drop is 0.7. If it's off, the current is 0. And the condition is when it's off, the voltage across the diode has to be less than 0.7. When it's on, the current has to be positive. In this case, let's assume the diode is on, because we've got 5 volts trying to push current through it. In that case, this becomes 0.7 volts, and the current is just 5 minus 0.7 over 100. Way easier than what we did last week. And if you compare, the ideal diode is a little bit wrong. The numerical solution from last week was 0.7588. Circuit lab was 0.7517. The lab experiment, when I ran it, was 0.768. Again, this is not going to be the correct answer. It'll be close. What we're trading off is a simple but close answer versus a much more difficult one to get. In my book, I use the ideal diode model for analysis. Then if I want to get a better answer, either simulate it or build it. Problem 2. Repeat the same 3-diode circuit that we had in homework set number 2, but in this case using ideal diode models. So I'm going to assume that this diode is on. I've got 5 volts trying to push current through it. The current is going down, so probably diode 3 is on. And this one's probably off because current's going backwards. If I assume that, then V3 is unknown. V2 is V3 plus 0.7. And V1 is 5 minus 0.7, 4.3 volts. So I really just have one unknown, V3. If I do that, I can set up one equation, one unknown, solve for V3, and I get V3 is 2.633 volts, V2 is 3.333 volts. And kind of the way I did that is I write the node equation. At V3, this current plus this current plus, well, this one's off, plus this current, which is right here, equals 0. And if you note, with an ideal diode model, V1 is not exactly 4.3 volts. V2 is not exactly 3.33 volts. It's close. A little bit wrong, but close. And again, what's nice about the ideal diode model is it's a fairly simple circuit to analyze, and it'll get you close. To get more accurate, throw it in Circuit Lab. Our problem with the ideal diode model is I've got 3 diodes. Each one has 2 states, on or off, give me 8 permutations. One of the 8 is correct. If you guess the right answer, you only have to analyze one of the 8. Otherwise, you just guess again. Eventually, one of them is going to be right. In this case, to check, you see V3 is 3.33 volts. Sorry. 2.63 volts. 3.33 volts. This is 2.63 volts. And so checking. Let's see. This diode is reverse biased. It's got minus 1 volt across it. That checks. The current through this diode, 4.33, is more than 3.33. So I have current flowing through this guy. Diode 3 has positive current. That checks. And that current's got to come from somewhere. Diode 1 is positive current. That checks. So my assumption was correct. LEDs. If I have an RGB LED, I can set the current by adding a resistor in series. If I want to produce this color, sky blue, then I want the red LED to be 7411 millicandles, meaning I want this percentage at full brightness, this percentage at 20 milliamps, 14.8 milliamps. If I have 14.8 milliamps, the red LED has a 2 volt drop across it, and silicon diodes are 0.7. Red LEDs aren't silicon. The material tells you the energy gap, which tells you the color. It's 2 volts. So this is 2 volts, leaving 3 volts across the resistor. 3 volts at 14.8 milliamps is 202 ohms. The green LED For 10,000 millicandles, I want that to be full brightness, full current. 3.2 volts across the diode gives you 1.8 volts across the resistor. 1.8 volts at 20 milliamps is 90 ohms. And the blue LED is 90.90 millicandles. It's this percentage of full brightness, that percentage of full current, 18.98 milliamps. 1.8 volts at 18.98 milliamps is 94 ohms. So this will produce sky blue. Problem 5, same idea. Change the resistors, change the color, and this will give me olive green. Problem 5, an AC to DC converter analysis. Given this circuit, find the voltage of V1 and V2. Now V1 is going to charge up and then discharge, charge up, and discharge. The peak is going to be 19.3 volts. That's the 20 volt peak right here, minus 0.7 volts across the diode. Doing worst case analysis, if this is 19.3 volts, I've got 19.3 volts across 120 ohms, give me 160 milliamps. For this capacitor, I equals C dV dt, 160 milliamps at 1,000 microfarads for 1/60th of a second, and a half-wave rectifier, gives you 2.68 volts. So this distance is 2.68 volts. And the DC voltage is the peak minus half the AC. DC voltage will be 17.96 volts. No, 14.96 volts. No, 17.96 volts. So this is 17.96. That's the DC voltage. And this is the AC voltage in units of peak to peak. At V2 then, I just have a voltage divider DC, 100 over 100 plus 20 times 17.96, giving you 14.96 volts at DC. The AC voltage, convert the inductor, capacitor to their AC impedance at 60 Hertz, put these two in parallel, then have a voltage divider. The input at AC is 2.68 volts peak to peak. Doing voltage division times the input gives you 0.205 volts peak to peak. That's the AC voltage. So at V2, it's going to have a little bit of ripple like this. The average is 14.96. The ripple is the AC voltage, 0.2 volts peak to peak. That's what I predict based upon my analysis. Throw it in Circuit Lab and simulate it. Here's V1, here's V2. Take the peak and the minimum. The average of the two is the DC voltage. The difference in the two is the AC voltage in units of peak to peak. Likewise for V2. And what you'll see is what I calculated is similar to what I simulated for the DC. AC is a little bit off. The reason it's a little bit off is V1 looks like this. This is actually a hard problem to solve. So what I'm doing is I'm changing the problem. That's a very typical engineering solution. If you have a hard problem to solve, change it. I'm going to change it so that I have an AC signal, constant of sine wave. I know how to analyze sine waves. I'm going to change the problem, but I need to change it in a way that I keep the flavor of the old problem. I keep the same DC voltage, keep the same AC voltage peak to peak, keep the same frequency. So if I pretend the blue line is a 60 Hertz sine wave with the same peak to peak voltage, same frequency, same peak to peak, same DC, almost the same problem. It's not the same problem. It's a little bit different. So likewise, these answers will be a little bit different. But get you close. If you want to get closer, I need to use Fourier transforms. That's the topic we'll be covering later. It's also covered in Signals and Systems, or use Circuit Lab. Problem 7 is analysis. Find C1 and C2 so that this is 2 volts peak to peak, and V2 is 250 millivolts peak to peak. Now I know what V1 looks like. V1 is going to look like this. The peak is 19.3. That's your 20 minus 0.7 volts across the diode. The minimum is 17.3. Gives you 2 volts peak to peak. The average then is 18.3 volts. That's the DC voltage. I can find the current then. The current is then 18.3 volts over 120 ohms. That's the DC current. From I equals C dV dt, I know the current, I know dV, I know dt, solve for C1, 1271 microfarads. To find C2. A couple ways to do it. What I like doing is assume C2 equals 0, find the ripple of V2. In that case, at 60 hertz, this is J565 ohms. By voltage division, I get 346 millivolts peak to peak at V2. I want it to be 250 millivolts. So C2 needs to be smaller than 100 ohms. It needs to be this much smaller, roughly. This needs to be 72 ohms. If I make the resistance smaller, this actually be minus J72 ohms. Make it smaller, the ripple gets smaller. So to get minus J72 ohms, C needs to be 36 nanofarads. And there's your design. Checking in Circuit Lab, there's your V1 voltage. I designed for 2 volts peak to peak. I actually got 1.84 volts peak to peak. A little bit wrong because I'm assuming this goes straight up and this distance will be 2 volts peak to peak. Actually, the diode is turned on for a small time, so the ripple at V1 will be slightly less. I have a slightly conservative design approach. DC voltage is pretty close. At V2, I designed for 250 millivolts peak to peak. I actually got 260 millivolts peak to peak. Got a little bit wrong. V1 is wrong, so likewise V2 is going to be wrong, but it's close. If you want to get closer, I can use this and iterate. I've got too much ripple. I need to make C2 a little bit smaller. But that's homework set number 3 for ECE 320.